Good morning, everyone. Today we're doing Unit 5, Lesson 1, Graphs of Sinusoidal Functions. So we're going to continue exploring sinusoidal functions, continuation from looking at them on a Cartesian plane like we did in Unit 4. So first we're going to look at state for some of these ratios. So it says state the exact value for the following ratios. So when they're wanting us to find the ratios and they're saying the exact value, we should be thinking that we already know these values. And these values are going to come from those special triangles we discussed in Unit 4. So we looked at two types of special triangles. We looked at a 30, 60, 90. And we need to memorize what the side lengths are of a 30, 60, 90. So the side opposite 30 is 1. The side opposite 60 is a radical 3, and the side, my hypotenuse or opposite my right angle is going to be 2. Okay, the other special triangle that we learned was a 45, 45, 90. So that's where both angles are 45, and the sides opposite both of them are 1, and our hypotenuse, or the side across from our right angle, is a radical 2. Okay, so we're going to use those special triangles to identify the exact values of these ratios. So the sine of 30, when we think sine of 30, we should be thinking opposite over hypotenuse. So if I look at my sine of 30 in my special triangle, my sine of 30, my opposite side is 1, and my hypotenuse is 2. So the sine of 30 is going to equal 1/2. Okay, for the cosine of 45, same idea, it's my adjacent. It's our adjacent side over our hypotenuse. So if we look at our 45-degree triangle, that's going to be 1 over radical 2. And then this cosine of 240, that's going to bring us back to the idea of our related acute angle that we looked at in the last unit. So we have to think about, where is 240 degrees located? And that's going to be in quad 3. So if I was to draw that 240 on my Cartesian plane, okay, 240 is going to be somewhere here, right? Because the first quadmaster is 90, second one is 180, and then into the third for that 240. So if that's 240 degrees, then we know this related acute angle right here is going to be the difference between 240 and 180, which is 60 degrees. So this little angle in here is 60 degrees. So now all we have to think about is, okay, what is the sine of 60? So if we come back to our special triangle, if we're talking about the sine of 60, is going to be radical 3 over our hypotenuse, which is 2. So radical 3 over 2. And then we just have to decide, is that going to be positive or negative? So if we think back to our cast rule, C-A-S-T, only my tangent is positive in that quadrant. So that means we're going to have a negative ratio for sine. Okay? So just important to be able to remember where we get those exact values from as we start looking at a sine and cosine function. So we're going to take a look at this angle theta, and we're going to discuss how it changes corresponding to each trig ratio. So if I was to set up these triangles, and I was to say that this triangle, this red triangle, was a 30, 60, 90 triangle, I could label the side lengths just like we did above. So my side lengths would be 1 across from 30 degrees. It would be radical 3 across from the 60, and we'd have a hypotenuse here of 2. Okay, so the table is asking me to complete the following table using our exact values for each ratio, and then use a calculator to get our decimal value. So if we wanted to start with our exact values for the sine of theta, well, if I'm going to start within this triangle, we'll start with 30. We'll come back to this idea of 0 in a minute. But if I wanted to find the sine of 30, well, the sine of 30, like we said up there, up top, is going to be 1/2, which is our opposite over our adjacent. So something to remember here, this 1 represents the y value of this point here, okay? And the 2 represents the radius of this circle, right? So recall we've talked about in the last unit that when we're trying to find the sine of theta, that's going to be equal to the y part of a coordinate over whatever the radius is that we've created, okay? And our cosine of theta is going to be your x value over your radius. So we could draw triangles all the way around this circle, or we could just recognize what's my x value, y value, and what's my radius. So at this point on my Cartesian plane would be represented by a radical 3, right? Because I went over radical 3 and then up 1. So if I needed to find the sine, I could just take my y value and put that over my radius, and that'll give me the sine of theta. All right, if we look at this other blue triangle, okay, now we have a 60-degree angle and a 30-degree angle up here. So again, we could label those side lengths. Remember that 1 is opposite the 30-degree angle, radical 3 is opposite the 60-degree angle, and our hypotenuse is 2. Well, remember, I said that sine is equal to the y value over your radius. So this time, this point is at, my x value was 1, and my y value was radical 3. So if the sine of theta here, the sine of 60, is going to be my y value, which is radical 3, over the radius, which is 2. Okay, we could continue on around the circle like this. Instead of drawing triangles, we could just make additional points. So this point, notice that all my radiuses are a length of 2. Okay, so we know that no matter where you draw a radius in a circle, it's going to be the same. So this point here, right at 90 degrees, is going to be 0 on my x and 2 on my y. All right? And then we can follow this around. We can see that this blue triangle is mirrored over here to be like the blue triangle over here. So this is going to be a -1, radical 3. And then if we wanted to draw that red triangle again, right, with my 30 degrees, it'd be somewhere here. And then we'd have a point of negative radical 3 and 1. Remember that negative radical 3 would be my x value and 1 would be my y value. Okay, go ahead and pause the video and see if you can put in the coordinates of the points as they would fall in each of those quadrants. So for quadrant 3 and for quadrant 4. So here is all the coordinates around the circle pointed in. Notice that each of these angles is an increase of 30 degrees, which is what's representative here in our table. So if we wanted to find the sine of 90 degrees, again, the sine of the theta is going to be equal to y over r. So if I look at where 90 is, which is the y-axis, the positive part of the y-axis, my y value is going to be 2, okay? And my radius, again, is going to be 2. So that tells me that'll reduce to 1. Okay, if I wanted to look at 120, 120 is that next angle, so 30 degrees past 90, so that's right here. So now we're looking at this line. So again, when we're trying to find the sine of an angle, it's always going to be your y value over your radius. So in this case, our y value is a radical 3 over 2. Okay, if we wanted to look at 150 degrees, again, that's going to be my y value. So that 150 degrees is the next line, the next 30 degrees. So right there is the angle for 150. So it's going to be my y value of that coordinate, which is 1, over my radius, which is, again, 2. The last point we want to make is for this 180 degrees. So 180 degrees is right there along the x-axis. We have to think about what's the coordinate at the end of that line. So the coordinate is going to be the same as my radius, which is 2. In this case, it's a -2, and our y value is 0. So when we're trying to find the sine of 180, it's going to be my y value, which is 0, over my radius, which is 2, or 0. Go ahead and fill in the rest of the table for the exact values, and then use your calculator to find the decimal values as well, and we're going to round to 3 spots after the decimal. Okay, so there's the values for the rest of your table. Hopefully, you can see a pattern that's occurring there as we go from 0.5 up to 0.866 to 1, and then back down to 0.866, back down to 0.5 and 0, and continues on that number pattern. I just wanted to point out what happens at 360 and at 0. We looked at 90 and 180, and it's similar. So if this is my 0 on the positive side of my x-axis, and it's also 360, right? Because if we go around the circle counterclockwise one time, we're going to end up back there. So the coordinate here, again, is going to be 2, 0, right? The radius is 2, so that's our x value there as well. So for the sine of theta, it's going to be my y value, which is 0, over my radius, which is 2. So that is 0, which is why 360 is also 0. Okay, so go ahead, I'm going to pause it again. Plot these points on the graph, all right, with your sine theta being along your y-axis. So those are all your y values, and your angles, or your thetas, going along the x-axis. So there's what your graph should look like. Okay, the sine curve starts at 0, works its way up to 1 at 90 degrees, and then comes back down to 0 at 180, back down to -1 at 270 degrees, and then back up to 0 at 360 degrees. So you should just know the general shape of the sine curve. Okay. And notice that it starts at 0. Okay, that's what we call the axis. We're going to get into some of the features of the graph on another day, but notice that it starts at kind of the middle point vertically of the graph, then moves itself up, back down to that middle point, and then moves itself down, right? And we'll explore the features of that graph later. We're going to do the same thing now with our cosine function on the next page. If I was to go back to my table on my first page, remember how our sine of theta was equal to our y values over r? Now our cosine of theta is going to be equal to our x values over r. So if we were to use this circle again, we're going to plug in our x values over our radius when we're calculating the cosine. Okay, so you're to complete the following table using exact values again. So this time, if I was to go back, okay, so if I was to do that for 0, if you had that circle in front of you, all right, your cosine of 0 would be 1, because your x value was 2 and your radius was 2. The cosine of 30 degrees, your x value was a radical 3, and your radius was 2. Go ahead and pause this video and fill out the rest of this table of values, including the exact the decimal values underneath, and then plot this graph on the curve, okay? So complete all the way to the end of number 4, and then we will get back together. Okay, so here's what you should have for your table of values, and then also your graph. And similar to the sine function, you should know the general shape of cosine as well. Remember that I said sine started at that midpoint vertically of the graph, started at 0, and then worked its way up and came back down. Well, the cosine function starts at the highest point, which is 1, and then works its way down to 0, and then down to -1 before it starts to work its way back up. So it looks more like a U, whereas the sine function looked more like a wave. All right, so we're going to continue comparing these two graphs, but it's important to become familiar with what they look like for each of them. So your trig properties of your sinusoidal functions. The period is going to represent the length of one cycle. So when we're talking about one cycle, it's basically how long does it take for the graph to get back to a repeating position. So if you were to look at our cosine function, it starts here and then it works its way down, right? It works its way down, decreasing, decreasing, until it starts increasing again at 180 degrees. All right, and it doesn't come back up to 1 again to make that repeating pattern happen again until 360. And the same is true of the sine function. So the period is usually 360 degrees. When we get into transformations, we'll see that we can change the period, but the general shape for sine and cosine has a period of 360 degrees. The equation of the axis is the horizontal line halfway between the max and min. Okay, so for both of sine and cosine, until we start transforming it, halfway between the maximum and the minimum would be 0, because our maximum is at 1 and our minimum is at -1. So the equation of the axis is y equals 0 in this case. But again, this can be changed with some transformations. And then finally, the amplitude is another important criteria. So the amplitude is the vertical distance from the axis to either the maximum or the minimum. So if we were to represent our axis of symmetry, we would draw a dotted line like this. Okay, and this represents our axis, which is at y equals 0. And then if we wanted to show our amplitude would be the distance from that axis up to a maximum or a minimum. Okay, so here's my axis here. If I wanted to go down, that would represent my amplitude. This would represent my amplitude. Okay, so in this case, our amplitude is equal to 1. Right, that's the distance from the axis to the maximum or minimum. All right, and then there's just some trig properties we should know in terms of sine and cosine. So for our sine function, our maximum value was a +1, our minimum value was a -1. So max was at +1, min was at -1. Okay, the same is true for our cosine. The max was at +1 and the minimum was at -1. Our zeros for our sine, these are very important, as we should recognize how they'll change when we make transformations. So zeros are at 0, 180 degrees, and 360. Whereas for our cosine, we only have zeros or x-intercepts at 90 degrees and 270 degrees. Okay, the rest of this is all the same until we start getting into those transformations. So we're going to have a period of 360 degrees. Our axis, which is that horizontal line that cuts the graph in half, is going to be at 0. They're going to have amplitudes of 1, and the domain will be all real numbers. And then our range will obviously be affected by those maximum and minimum values. So our range will be -1 less than or equal to y, which is less than or equal to +1, where y is for all real numbers. Okay, that's it for your note for today.